Okay, so when you first start up any logic, you'll likely be presented with this screen here. Um, uh, this screen has a lot of example models that may be of interest to people with respect to your projects, giving you ideas. We also have something on the order of about 80 to 100 models that we will be providing you, to which we'll be providing you links. We should check if that link to those is actually in the syllabus right now. If it's not, what's that?
Okay.
Otherwise, we'll make sure it's on Canvas. But example models here and tutorials are things that you might want to make use of in ramping up your understanding for projects and particular methods. Today, we're talking about system dynamics, and we're going to be building our first model from scratch. So what I'd like you to do is on this screen, if you have this up, minimize this using that small little widget there. And many of you may have encountered the overall framework we're using here before. If you've ever used Eclipse, which used to be a central IDE, a central integrated development environment used in software development, you will have encountered this framework before. And a lot of the interactive metaphors that you can use here are just Eclipse metaphors. So that used to mean more to students because they were thoroughly versed in Eclipse from other classes. Probably less so your generation, but just be aware that we are in an Eclipse environment, and the general rules for interacting with the windows and so on, minimizing them, full screening them, zooming out from full screen back to no longer being in full screen, etc., are those inherited from the Eclipse. So if you're in this environment, you'll notice that we're going to situate ourselves with certain windows being commonly used. Most of you are third year, fourth year computer science students, so I'm not going to belabor this point, but generally we're going to have a properties window up. We're going to have a canvas on which we're going to be building declarative components that make up a model. And we're going to have a projects window over on the left that will give us the structure, what we might call the static structure of that model, the components of its specification. Commonly, I'm going to include a palette underneath that, and I'll switch back and forth between them. This palette is going to have the pieces out of which we're going to build up the model. Okay. But the principle of system science, all the techniques we're covering this semester are system science techniques. And an important principle of system science is that it's not so much the pieces, but their interconnection that's the most important matter. And so really the art of model building is not going to be in just jumbling together a heap of these pieces from various sub-palettes, but really connecting them together in manners that are artful, that skillfully build up an entire model. And like the systems we're simulating, these systems we're building will typically be nonlinear. The whole will be greater than the sum of the parts and will have very different behavior if you consider two things together than you would get if you consider each in isolation and summed up the behavior. Okay, but enough on the sort of high level situating ourselves. Let's dive in here to build up a model. So we're going to go here and we're going to create a new model, okay? And this model is going to be called SD for system dynamics, okay? Diabetes prevention and treatment, okay? And I'm going to name it V1, okay? Now, it's extraordinarily important that you pay attention to model time unit. It's also important that you recognize that what model time units represent. Those are not time steps. They dictate instead the meter stick, as it were, by which we measure time. It means 1.0 would mean, if we were to keep it at seconds, 1 second. And that's not going to be a convenient one for us in which we could specify the model. We could specify a model in that, but we're going to choose the yardstick to be years, as it were. So 1.0 units of time will be 1 year. That's how we'll interpret it, okay? Again, it does not mean, and I emphasize this, it does not mean that we're going to be hopping forward in 1 year increments, but rather that's going to be our standard by which we measure time. Okay, so having done that, I pressed finish, and you'll notice over in the projects window, for some reason it switched me to palette briefly, but over in the projects window, it's now populated with some basic components. And I'm going to be building up this model bit by bit through successive versions. Okay. Does anyone need the help of our exceptional TA? Exceptional and talented. Exceptional and talented. Yeah. DJ. Okay. Second row. Middle sector. Okay. So we're going to have this model built up out of these pieces. And the first of them is this one called Maine, which is this global environment, this an entire environment in which we're building things. And for aggregate system dynamics models, that's where we're going to undertake our actions. You may remember from our previous exercises that we had other things. We had like a person agent. And for agent-based modeling, and some for discrete event simulation, we'll often add additional types of actors of various sorts. People, service dogs, physicians, or what have you. Here we'll typically work in Maine, okay? It's not that you couldn't add something in a hybrid model. We might have system dynamics models at the level of an agent, for example, but we'll approach that later. Okay, now, so we're going to be building in this canvas of Maine. And we're going to build up sort of in this area delineated by these lines here. I'd like you to go to the palette. And now I'd like you to go pick from a subpalette. And it's this one called System Dynamics subpalette, okay? It's really oriented mostly to a specific sort of system dynamics model and English talking about, but it can be used to build up causal loop diagrams as well. And I'd like you to select that system dynamics palette. And you'll see the various building blocks out of which a system dynamics model is built. And from your words, not 15 minutes thence, you identified some of them. Talk about stops and flows and auxiliary variables and parameters. And we're going to be availing those. Okay. But my focus here is going to be about how they work together to form greater wholes. And to use it to teach the principles of evolution, the ways in which the structure of this system dictates its behavior. And that's going to be a principle we're going to see writ large across the entire course. Structure determines behavior. How we describe that structure will be different for each of the 3 types of modeling. But in each case, structure will govern the possible behaviors of the system, and parameters will tune it within those possible behaviors about which of them actually end up being exercised. Okay, So let's bend our backs to the task of putting in place structure. So we're going to build up structure from this palette. And the first component is we're going to add in a stock. So we go over here, click on it, and drag in and drop. Okay. And this stock is going to represent our focal population for the first few minutes. We're going to call it normoglycemic population, meaning the population with kind of normal levels of blood. So give me most people in the population, as it turns out. But if that's a bit long for you, you could call it NG population. Okay. And the point is, it's going to be an aggregation. It's the value of that stock is going to be a count of people at any one time who are in it. Okay. So in order to specify this stock, we need to specify one piece of information initially. It's initial value. After that, its evolution will be dictated by what? We specify its initial value. That will start it off with a certain state, a certain number of people there. And what's going to dictate how it evolves over time after that? Yes, flows. Right? Flows indeed. Flows in the inflows and the outflows. And specifically, the net flow. Going to indicate its rate of change, how quickly it's rising or how quickly it's falling. Okay. So we'll put in a value here of 40 million. So that's 40 followed by 7 zeros. Count them. 4 0 0 0 0 0 0 0. Okay. About 40 million people together. So I'm just putting that. Oops. Okay, we don't need the new line after that. So that's its initial value. If I were to run this model now, what would you see happen over time? Nothing. It's, yes. So Pius and Aiden. Thank you. Okay. So it would exhibit no behavior. It will be a static system. This is a static system. It's not changing over time. There's no down, or there's a fixed down invariant down. Okay. So to add something, to add some dynamics, we're going to put in place a flow. Okay. And we will go to the flows here and we'll drag this in. And this can be a bit tricky. So I want you to watch it. It's not a super substantive thing, but you got to learn how to handle these pieces with facility in the metaphors here. So you're going to click on this, drag in, and it's going to form this kind of gangly articulated arrow. And you're going to go, watch the front of that arrow. Right now it's white. And you're going to drag it over and it's going to turn green. And green is the color and state charts of the game. So you're going to want this to be connected to it as an inflow. Now, if you somehow miss the target, you'll be stuck with it in a disembodied sort of way, a flow between two flows, which has its utility mathematically as a unit flow, but I'm not going to get into that. Okay, so we can then drag this in there and make sure it's green. Make sure it's connected. It's easy to miss, get close, but it isn't actually connected. Make sure it's green. Green is going to indicate it's connected. And we're going to call this flow, make sure you select the flow up here in properties, and it's going to be called births. Okay? we have to give for flows, not an initial value, but a what? What do we have to give for flows? Can anyone speak up? Sorry? What do we have to specify for flows? For stocks, we have to specify an initial value. What do we give for flows? A rate. A rate. Yes. Name Eric. Eric. Thank you. Okay. Somehow it'll sink in through this thick premium. And maybe by the final day, I will remember. Okay, thank you, Eric. Thank you for your company. Okay, so we're going to need to specify a rate and a formula for the rate. In general, that rate will depend on the state of the system. Let me say that again. Very important point. How the system evolves in general is going to depend on its current state. What is now is going to depict how it will change over time. That's what makes it what's called a dynamical system. It's not that it's just changing in some fixed way, in some determined, totally fixed, invariant way over time that never changes. It's not that it's just totally random with no sense, with the same random process over time. Dictated by stochastics that don't change. No, how it changes depend on its state. And this is in general true for flows. Right now, this happens to be a fixed value. In general, that won't be the case. In general, this will depend on the state of the system, and we'll see that soon. But let's suppose it is zero. What would happen if we ran this model? What would we see? Nothing. Yes, Nate?
I didn't actually say anything. I just wrote it on there.
Yes, well, your hand was a fine hand raised, and I want to acknowledge that.
That's Alex.
Alex, thank you. So you're going to say nothing as well. Yeah, nothing is going to change because the inflow is zero. The stock is not going to change over time. Its rate of change will be zero, right? The net flow is zero. That dictates its rate of change. How many people will be rising per unit time per year? Are we okay with this? Okay. So let's make it something other than zero. May I? May I? Okay, hearing no objections. I'm going to change this to, I'm going to say 1,000,000, one followed by one followed by 6 zeros. Okay. Now I say 1,000,000, but what does that mean? 1,000,000 what? There are 1,000,000 people, but it's not 1,000,000 people. It's 1,000,000 people what? Nate? Robin? Per year. Per unit time. That's how we measure flow. All flows are per unit time. I think someone up here said it earlier. They're quantified per unit time. So if we have a stock that's saying people, this will be people per year. If the stock was in dollars, this would be dollars per year. The stock within doses of vaccine, this would be doses of vaccine per year. This is cumulative infections. This would be number of new infections per year. Per unit time. This is very important. It doesn't make sense to add the value of the stock with the value of its flow, because that's like adding a square foot to a linear foot or something like that. Or a position to a velocity. Doesn't make sense. It's mixing different units. Okay. So if we have that be 1,000,000, what do we expect to see for the value of this stock over time? What would we see? Again, it's a good thing to sort of, models are thinking tools. They help us think more deeply, quickly, thoroughly, and reliably through the consequences of our duties. So the model sort of captures a theory of how the world could be, and we can see its consequences. So what will we see as a result of this?
Over
This
there.
is $1 million per year, yes, okay, okay, I'm. Aiden,
Yes,
okay,
the neuroglycemic population will continue to rise by a million each year.
okay, good, and so it will be going up or down over time?
Up.
Okay, okay, so let's test Aiden's theory for how the behavior will change. So we're going to click on this and we're going to use this little thing here, and there we see it. As Aiden has characterized it, it rises like the sun in the east, right? It's rising over time. So as time passes, that's the x-axis, the number of people in the stock. Started at 40 million, it's rising 70 million, 72 million. The Northwest Territories is being populated, new cities spring and none of it. No, okay, so we had a stock, we had a flow into a stock, and that induces behavior in the stock. We could alternatively go look at the value of the flow. The value of the flow is constant and the stock rises on a continual basis. Does this make sense? This is the rate of flow, but it's also, because it's the net flow, there's no other flows in and out, it's the rate of change of this stuff, right? Over time. Is this making sense? Stepping back, this stock with only one flow in, nothing out, the stock is accumulating the value of that flow. Plus, it had some initial value, 40 million. And after that, it's just accumulating, it's just rising. Does that make sense? Are we in sync here? Okay, then let's take this one step further. This model is a dynamic model, but you could be forgiven for saying, well, this ain't no dynamic system, like what you said. A dynamic system is something where its behavior over time depends on its current situation. And its behavior over time here does not depend on its current situation. Its behavior over time, as evidenced by the change in the value of the stock, is actually fixed, right? It's rising at 1 million per year. Does that make sense? So this is not really true to the spirit of dynamical systems. It's kind of to call it a dynamical system is a stretch. So let's do something a little bit different. Let's put in an outflow if we could quickly. And we're going to actually have the outflow depend on the state of the system. Okay. So I'm going to go to the palette here, and I'm going to drag in a flow. And this flow is going to be, as sometimes happens, a somewhat truculent flow. So I'm going to drag that in. I'm going to connect it to be an outflow from that stock. Okay. And it is going to be called I'm just typing right here, normoglycemic deaths. You'll notice there's a couple things, some more superficial than others. The first thing is, I started to type it there. If you can't type it there because you lost focus or whatever, you can go and put it in the properties window, have it in the properties window and name the thing. So that's one thing. One point. A second point is that it kind of lands up on top of that. And because it's highlighted right now, you've highlighted this, you'll notice it's underlined this, meaning you could drag it around. And you probably want to do that. A third thing to notice is I actually named this with some malice aforethought. I named it with a lowercase n rather than the capital N of a stock. Naming matters. If you take 371 from me, software project management, I care a great deal about names. I care about names being intentional revealing. Being things you can look at and you know what it's about. You can remind yourself. Maybe the person who learns what it's about is a stakeholder who wasn't there to build the model, doesn't know all about the rules, but can look at it and critique it, and they know what it means. You know, different things are labeled in clear ways. Or maybe the person who sees what this is about is yourself in the future, and you're reminded, oh, this flow is called that, etc. Names carry significance, and in this course, I expect good naming on your projects, and I will give you feedback on your naming of things. You notice I named it lowercase because I use lowercase for the flows. So if I see a list of names, I know which are stocks, which are flows, and I can easily pick from the list which are them. Okay, normal glycemic test. Right now it's 0. So what will this stock do? If I were to run this model right now, what will it do?
Nothing.
Well,
Because the rate will be zero, something like that.
okay, so the thought was it will do nothing. Might anyone differ?
I mean, outflow will be nothing, but the rate of increase will be seen.
Yeah, it'll be exhibiting the same change name
How much?
and the. Sure, thank you. Good. So it'll be exhibiting the same rate of change as before, because we've just added a flow that doesn't change the net flow at all, right? And the value of the net flow is given by the rate of flow of bursts, people per year, minus the rate of flow of this outflow, right? 0. Are we okay with this? Okay, now let's be true to the spirit of dynamical systems. And let's change that. Okay. Let's change it so the rate of outflow depends on the state of the system. If I may. Okay. So what I'd like you to do is to put in place a formula for this. Now, but this formula is going to depend on an assumption. And an assumption is something that we want to make explicit. We want to make it very clear we've made this assumption. And we use a very specific construct in any logic to encode our assumptions called a parameter. Okay? A parameter describes this. It actually does more than describe. It actually communicates that assumption from the point of creation of what you're working on. So if we put a parameter here, the thing that creates main, which will be the scenario, is going to communicate. Later, that statement will have added significance. So I'm going to have a parameter, and I'm going to drag it in. And this parameter, which I'm also going to name with a lowercase, is going to be called mortality rate among, you could call it NG, I'm going to call it normal glycemics. Okay. Okay, so I'm going to specify a mortality rate among these normal glycemics, okay? This is going to be a rate of mortality. And this is going to be as a rate. It's okay. So I need to be clear, and you're going to need to watch this because this is a very common area of confusion in the field. When people use system dynamics, they be very careful about how the term rate is used. I spoke earlier about the rate of this flow first, right? What was that measured in? Yes,
People per year.
people per year. Good. I talked about the rate of this outflow, also in people per year. Now we're going to talk about mortality rates. And this too is going to be a quantity per unit time, but it's not going to be people per unit. It's actually going to be some probability per unit. And probability actually does not have unit people. It has unit, it's what we call dimensionless. It's what we call of unit dimension. And so this is going to be a rate per person. That's probabilities that they die per year. So I'm going to put in 1.0 divided by 85, meaning 85. So this is a probability per year that someone will die. Okay. And you'll see the same form occur again and again. 85. Does anyone know what that represents? It makes you see one. Well, I might have sent it over 233. What does 85 mean? Anyone? Yeah.
The chance or the average.
Yes, it's the average lifetime it's going to be. And we'll see the form that gives rise to this in the formula for this flow. So, with your leave, I'm going to go hitch up. I'm going to put a formula in this flow. When we give a formula, this is quite important, and it's a principle of system dynamics. Principle of system dynamics says that not only should models be declarative, you specify what you want to characterize and let it figure out the how, but more than that, if you look at a model, you should have the option of seeing it at a high level or burrowing down and seeing the detailed assumptions in the form of values of parameters in the form of formulas. So what you should see is the structure of the model. And one element of this structure is how stocks and flows are arranged. But another one is how, for a given quantity that requires a formula, like here, a flow, later it will be auxiliary variables, on what it depends. That's an element of its structure. The interconnections between things. So, what we're going to do is drag here links. We're going to drag in a links from, and it's going to be a links from the stock to the flow. Okay. And we're going to drag in another link from the parameter down to the flow. Notice in each case, that link indicated a dependency, that the formula for this flow will depend on two things, the value of the stock and the value of this parameter. Okay, make sure that they are direct, links are directional. They have a head to them, and that head should go into this. In other words, it's indicating how does this depend, on what does this depend? That's an element of the model structure that we want to illustrate. We want to show, make evident, make manifest. So those two links should go in here. And now we need a formula that enacts those dependencies, that has those dependencies. So the formula here, was it Eric? Yeah. Eric. The formula here is going to depend on these dependencies. What a horrid statement. I should feel ashamed for such a crude utterance. It's going to make use of those dependencies. Okay. I try not to inflict linguistic injuries to my classes. So this formula is going to be given by mortality rate. Okay, now this class is likely to enjoy past pleasure of acquaintance with autocomplete. Yeah? Is autocomplete your friend? And it is mine. Yeah, I know. It can be your enemy too sometimes. But for those who are not aware of it, if you start typing out mortality rate, make sure it's capitalized appropriately, just like it's there. And you press, okay, on these computers, it will be control space. If you're working with a Mac, Wade will enunciate in a stentorian voice what the corresponding,
Option space on a Mac if we want.
yes.
Include a couple in this class.
Okay, so appropriately stentorianly dictated. So, mortality rate among normal glycemics times normal glycemic population. Okay, there. Okay, let's break this down. Let's be clear about what's going on. We have some number of people who are at risk of dying. If that number were 0, the number of deaths per unit of time will be 0. If there's no one at risk of dying, nobody's going to die. But for each person in this state, there's going to be some probability given by this mortality rate among normal glycemic probability per year probability of them dying. And that's why it's this formula is going to give us people per year. That's the unit, or I can probably say, yes, people per year is the unit of this flow. And to get it, we multiply a number of people times a probability, that's dimensionless, of unit dimension per year. So 1 over a year is the unit of this times number of people, you get people per year. You need to start paying attention to units in this class. If you haven't made heavy use of them in your other classes, you will here. And you will find they are your friends, even more reliable, I might add, than other people. Okay, so we have this formula giving how this depends on the stock and the perimeter. I want to highlight that we've now built a model whose change at any one point depends on the situation in the model, the state of the model at that time. I said it earlier. Right? If there's nobody in that stock, nobody's going to die. If there's a billion people in that stock, there's going to be a lot more people dying than if there's 100 people in the stock. So the change that this model exhibits in terms of the values of these flows is going to be a lot different depending on the state of the model. So, for my exhortation to you, 20 minutes then, I'm going to ask, what behavior do you think will come out of this model now? Yes, Eric.
So I would start pretty linear and then it's going to taper off and then sell at a plot. Where the number of births, the number of deaths, the number of births in constant, and number of deaths based on based on the number.
Awesome job. Awesome job. And that's exactly right. So we're going to see some initial behavior and then it's going to plateau at some value where and Eric laid it out for us with alacrity that at that point of balance, the inflow will equal the outflow. Because the inflow equals the outflow, the rate of change in stock will be what? Okay. Okay, so let's investigate Eric's mental model and see if it holds true to the behavior generated by the structure of the model. So I'm going to be running this and I'm going to go look at this stock and I see that at first it seems to be rising and you may be excused for saying, well, it's just rising like before, but you'll notice a certain bend. You'll notice that it's exhibiting a rise that's sublinear. It's actually not rising totally linearly. It's bending. And as time goes on, it's actually plateaued. This is a bit hidden. This is a poor way of displaying it, but you'll notice essentially it's flat here. It's at 85 million. Because at 85 million, well, what will the inflow be? Well, what will obtain per Eric's recipe? At 85 million, what will be the case? If it's flat, if the number of people in that stock is flat, no longer changing, what must be the case? Eric laid it out. Inflow,
Right.
yeah. Okay, million deaths per year. Exactly, and that equals million deaths per year equals million births per year. And so it's inbound, right? It didn't go up to 85 million for no reason. It went up because that's the point at which it's inbound. Now, what if we had started this stock at 100 million? I know your image of Canada will be a lot different. Maybe I'll put an extra zero at its end. I'll make it 400 million instead of 40 million. What do you think is going to happen now? Will it rise and look like that? What will happen? It'll decrease until it plateaus. Because why will it decrease? Because the what is greater than the what? Greater than the inflow. Yeah. Or if I'm to put a fine point on it, the rate of outflow is greater than the rate of inflow. I mean, normally if we say the outflow, it's a rate, but we should be clear in our minds that it's a rate. It's a people per unit time. And it'll be greater than the outflow. But then what will happen? Will it forever plummet the number of people in that state? What will happen, young Pius? It'll reach the state of equilibrium at which what will obtain? At which what will be the case? Flow zero. And flow zero. Yeah. Okay, let's run it. I added a zero. And I'm going to run it. And we shall see it run like the wind. Okay, so here we go. We're gonna show it, and you'll notice again it's decreasing, but in a manner once again that's not simply going down linearly. It's going down slower and slower over time. And if we were to run it, and time passes, and empires rise and fall, it will go to a point where once again it's in balance. And what is that point? What is the value of that stock at which it's in balance? 85 million. Because inflow then equals outflow. Your name? G. Okay. Are we in solid ground? Are you feeling okay? Okay. Now, I want to emphasize something that may be evident to some, but new to others. And you'll have to forgive me if you, by the way, you can, down here, you can set the speed at which this model evolves. I'm going to set it back to speed 1 just for this illustration. And I'm going to plot this out. What I want to emphasize here is that over time, as we plot it out, this system will evolve, and it will evolve to this equilibrium. It is going to be evolving in a way that doesn't just go down linearly at the same. It will go down linearly if the outflow minus the inflow are always the same. It'll go back. It'll go up linearly. If inflow minus outflow is always time value greater than 0. But it doesn't. It changes because the rate of the outflow here is changing, right? Over time. It depends on the state of the model. And it's important to recognize that when we have these systems, that change, the rate of change in the outflow is going to depend in general on the state of the system. I have students who on my final exam, I thought understood this point. But then when I ask how it will evolve, they just say it will go down in some fixed way and it will go negative, the number of people in the stock. The number of people in the stock, as Pius said, started high, it dropped, but it didn't go below zero. Why didn't it go below zero? Just to make this very evident. Why didn't it go below, why didn't it just go down, down, down and go below zero? Precisely. So as the number of people in that stock goes down, the number of people dying per year goes down as well. And it reaches equilibrium, where Gideon said, where the number of people is 85 million. Do you understand that point? This is an extremely important point that somehow some students tend to miss, some students tend to miss on the final exam. I just want to be very clear. It really matters that its behavior depends on the current state of the system. Are we okay with it? Okay, now let's continue. So I've been talking about inflows and outflows, right? And it's an extremely important point that the value of the stock will rise if the inflow is what compared to the outflow?
Greater than the
Greater. Yeah. The inflow is greater than the outflow, it'll tend to rise, just like a bathtub. Right? Or your toilet, if it's plugged and you have water coming into it, it'll tend to rise, right? If we were familiar with it. It'll go down if the what is greater than 1. If the outflow is greater than the inflow, or equally, per Aiden's comment, if the inflow is less than the outflow. It'll tend to stay the same if what? Equal. Right? Are we good with this? Yep. This may seem superficial, but if you watch behavior from the world and you're trying to interpret it, and you're watching something that's a stock, and you see it rising over time, you know immediately, for example, well, the inflow is greater than the outflow. And you can often start to reason, what does that tell us? Well, it means people are getting affected faster than they're recovering. And that's going to tell you something about what's going out there in the world about those quantities, even if you don't have data about them. Quantity like the value of the stock will tell you about what, how the relative values of things going into and out of it. Okay. So we're going to continue to build this up, though, with some additional flows here. Okay. 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 So we are now going to bend this flow to our will below this stock. We're going to drag it down there, and with it will come its flow. The flow, it's cloud. The cloud represents some exogenous destination outside the scope of it. What we're watching here is endogenous behavior of the model, behavior that it's producing for us, right, over time. And thus far, it's been modest in its form. I want to now add another stock, and it's going to be over here. And this is going to be undiagnosed diabetic population. Okay. People have diabetes but aren't yet diagnosed. They're not yet recognized. So and we're going to represent the incidence of diabetes, the new development of diabetes on a regular basis by having a flow from normal glycemic population to undiagnosed diabetic population. And if I had artfully arranged this, I might have been able to make it the width of one of those nice flows. I'm not sure often you can reason about how long that flow is, but I think I've overestimated how it is.
It's 4 squares.
4 squares, thank you. Okay. Excellent. And I didn't look who that was, but was that young Aiden's voice?
Yes, it was.
Okay. Thank you. Okay. So we're going to have developing diabetes here. And once again, we're going to need to prettify it by dragging that down. And once again, we're going to need to unify these two because they're standing next to each other without being connected. So near yet so far. So we're going to drag this over and put it on top of that so that the two are unified. So identify. So this will so make sure it's green. Green is the color. Here, there we go. And I'm going to actually just arrange this so that we can kind of spiff up this area. Okay, now this is going to be called, we're going to now drag in a parameter here, which is going to be, again, parameters encode assumptions. They make our assumptions evident, make them explicit, make them able to be changed easily, as we'll see in scenarios. So we'll be able to run the model with different assumptions. We can document them by creating an explicit parameter. We can give it well-defined units, etc. So this parameter is going to be called incidence rate of diabetes. Okay. And if I wanted to be careful, I might have named it annual incidence rate. You notice I'm playing this rate thing. A rate is always something per unit time, but this is a per person per unit time rate. And so we're going to have a similar construct here. In this construct, like autocomplete and like units will become your friend because it's called a first order delay. Okay. So it's going to basically be the same form as this. This is going to be a rate per year. And the number of people developing diabetes, like the number of people dying in general, will depend on the number of people at risk. Does that make sense? So can anyone tell me on what two things will developing diabetes depend? As a flow, on what two things will it depend? Yes, Akshina?
Yes.
Yeah. Exactly. So on two things, the value of the stock, normal glycemic population, and the incidence rate of diabetes. So we're gonna drag this over, make sure it's green. And on both sides, green here, it goes from this to this because developing diabetes is depending on the value of this parameter. It's also depending on the value of the normal glycemic population. If there's nobody at risk, nobody will be developing diabetes. And what is the formula here going to be? Anyone?
5 minutes.
Thank you. What is the formula going to be? Yeah. Yeah, times the normal number. And you've just discovered, and G. Henner's articulated, this general pattern. This is called a first order delay. This is the most common building block in system dynamics, other than like the most basic elemental things like stocks and flows and parameters. It's this higher level construct you see again and again. So I'm going to go to that formula and I'm going to go here and I'm going to put in incidence rate. Remember, autocomplete is your friend of diabetes. And what is it? Is it plus or times? Times. Because it's a chance per unit time or, chance per year times what? Times the normal glycemic population. You got it. Okay. Now, again, students sometimes get confused about this. Does this have to somehow say, well, only those who don't die right now will be at risk? No. Both these processes are occurring over time with a certain chance per unit time. And we simulated a very, very fine grained basis. Maybe it's at the level of a day or half a day. And there's some number of people dying, and there's some number of people on that small bit of time, that DT, that delta T. And there's some bit of time people developing diabetes. And those can go on in parallel with each other. And they don't, and it'll draw down the value of the stock, but as the stock gets to zero, the rates of these flows out, and people per unit time, the rates of these flows out will go to what? If the stock goes to zero, the rates of these flows will go to what? To zero. So the stock won't go negative. It's not like, oh, we have to take into account people are dying, we can't consider them here. No. They're both operating at the same time. There's both some infinitesimally small period of time. We're figuring out how many are going this way or that way, but it's actually just small numbers. It's not on a per person individuated basis. So if I run this, I have to give an incidence rate of diabetes on a per year basis. And I'm going to give you an incidence rate of diabetes of, and I had down a, 0.01 per year is what its time unit is. We actually are not going to yet be starting to mark these up. So 1% chance per year that someone will develop diabetes from. So what do you think the behavior of this model will be right now? If we run this, you'll notice I haven't put in like a death flow from undiagnosed diabetic population. What do you think the behavior will be of this? Yes, okay. Alas. Name? Alex. Thank you. Okay, you have to be careful because I'm going to start to think like, okay, Alex Abe wear orange shirts. That's all I'm going to do. And then it's like, it's Oakland. And then you're going to switch places and I'm going to, anyway, so Alex.
The normal glycemic population will plateau slightly lower if there's two outflows now. So if the overall outflow rate is higher.
Excellent.
Undiagnosed as with no deaths, so this skyrocketing.
Yeah, so this will be going up because all it has is accumulation, right? You should be getting this very strong notion that stocks with only an inflow accumulate over time. There's actually a word for it in calculus. What's that word? Any of you taken 116? What's that word? The value of the stock does what to the inflow? If it's just an inflow to it integrates the inflow over time. The inflow is its rate of change over time, and it is the integral of that inflow. So let's run that, and then we will have to switch to a final topic. Correct, Wade?
Yeah, I was off on my 4 minutes.
Okay, we need to say something about teams, right?
Yes.
Okay. Okay, so we're going to be plotting this out, and we will see per Alex's articulation this is rising over time, because all it has is people coming in, nobody's leaving, right? And the value of the normal glycemic population, per Alex's comment, is no longer going to plateau. Oh, you know what? I should have changed this back. I'm sorry. I put in this extra zero here to 400 million just for illustrative purposes. I'm going to change it back to 40 million. I'm sorry. I should have done that. Let's be operating with something that's not so hugely and wildly out of balance. So here we go. And initially this population, this normal glycemic population is going to be rising, but it's not going to be rising to 85 million as before. As Jihan noted, that because then it was inflow equal outflow at 85 million. Now, as Alex aptly noted, we have two outflows. An outflow will equal outflow at about 46 million. Something like that, it looks like, right? But it's going to reach equilibrium. Will this stock over here reach equilibrium? No, because it's just accumulating in flow, right? So this again is a model where the change over time depends on the state of the model. It's a dynamical system. And you've seen some of these building blocks of building up a stock and flow model. Now, if I had time, I would go add another construct here. I'm going to stop this. I would go add from the palette another construct. I would add a dynamic variable called population. It will be the sum of all the stocks right now, just of these two. And then I'd have the births be equal to the total population times the birth rate. And so we would have births that depend on the state of the model, the total number of people. But we'll have to leave further adventures with stocks and flows to another session. When the fall is cooler. Okay, so I do wish to say something. So you folks had expressed your preferences for teams for projects. UJET has remarkably created a system which represents those preferences, which represents the projects, which operates within the rules of the number of students per project. And so the number of students on the teams. And it also captures in its weighting scheme your stated preferences for partners. And we've come up with some team assignments for this. And we will be posting them this afternoon for you to look at. And we will send out along with that, the emails of each person on the team so you can reach out to each other. Some of you will know each other because you may capture some of these pairs, you'll already know each other. But other times you may be new to each other. We'll post those emails and you should reach out to your fellow teammates. Anything else, Wade, that you would like to say before we break?
Please submit your model files from this exercise on Canvas. Yes.
Okay. That's good. Okay. Okay, that's great. Yeah, we'll have people here. I will say that for when you turn in these models, really what we're looking for is engagement with them and that you followed along, with some measure of care. We're not going to be like seeing, does it do the right thing? Does it plateau at exactly the right level? But we will be looking to see that you would follow it along with some care and a sense.
Do you want like our name and SID and stuff like that and our submission somehow, like in the file?
That's a good question. I think it's going to be given with it, but I will ask Lucia, when they submit these, do they specify some text for their name and NSID?
No, because from pod, I can export their assignment with their SID and student number and name.
From Canvas? Canvas, okay.
Okay, so just hand in as is.
Yeah.
Yeah.
Okay, we good? Okay, okay, folks, so we're gonna continue our march through the additional forms of modeling over the next couple of sessions. And we'll be weaving together these interactive components to get you face to face with the building blocks and how to use them and some of the reasoning. Together with and have reflections on the videos. Okay?
One thing I need to mention is that don't submit screenshots. Don't also submit the model file. Don't submit like other related file for the model.
Yeah, just submit one ALP file.
ALP file.
The ALP, the model
Screenshot not
file.
there.
Yeah, the model file that's created by any logic, that's what you will submit, not screenshots, not artistic renditions or something like, but the actual ALP. And just that.
Yeah.
Okay. Thank you, everyone.
Office hours start now if you're available for that. If you want to talk to one of us and you can't stay for